Welcome again to everybody. I think we can start. And in the meanwhile, if someone else will join, we add to the webinar. My name is Stefania De Santi. I am project manager in APRE, the Italian Agency for the Promotion of European Research, and I'm the coordinator of the EIC Communities project. EIC Communities, together with the European Innovation Council, is organizing this series of webinars dedicated to the artificial intelligence, in particular together with the EIC Programme Manager Hedi Karray. I just spent a couple of words about the EIC Communities project. It is an Horizon Europe project that aims to support the EIC beneficiaries working close with the European Innovation Council, and want through a series of initiatives and the establishment of 3 communities of practice dedicated to clean tech, industry, and health to give visibility to the EIC beneficiaries and providing them initiatives to network with the relevant stakeholders and find new opportunities to cooperation and get even closer to the market. I invite all of you to visit our website, deepsync.eu. I will let the reference in the chat. And in this website, you can find all the EIC projects that are participating to our projects. So you will find a description of them and detailed information, but also the stakeholders that are part of our communities of practice. Furthermore, in the platform deepsync.eu, you will find all the webinars organized with the European Innovation Council and the Programme Manager Hedi Karray. You will find the recording, and also the today meeting, the today webinar is recorded. So you will find later on the registration on DeepSync, and you are going to receive a follow-up email after the webinar as soon as the recording is ready. So, dear Hedi, I let you the floor. So please, the floor is yours.
Thank you, Stefania. Hello, everyone, and welcome to this webinar in our series on webinars on AI innovation beyond the hype, aiming to understand with the community the current advancements, limitations, and future perspectives of AI innovation. Today, we'll be focusing on 2 aspects: AI in science and AI for science. We distinguish this to emphasize how AI is used in scientific research and the AI tools developed specifically to assist researchers in making scientific breakthroughs. Today, we are fortunate to have distinguished speakers with us, sharing diverse perspectives from research and innovation to business. Unfortunately, one of our scheduled speakers, Karina Prenkel, is unable to join us today for some emergent matters. It's a significant loss, as her insights on ethical issues would have been very interesting to her. However, we will still address ethical considerations during the webinar today. So to start, I will give the floor to my colleague Daniela Petkova, who will provide an overview of European policies on AI in science. Daniela is a policy officer in the AI in Science and Industry 5.0 and AI in Science unit at the Directorate General for Research and Innovation within the European Commission. Daniela, the floor is yours to provide to us the perspectives of the European Commission on the topic. Thank you.
Many thanks, Hedi, and good afternoon to everyone. Thank you for the invitation. It's great to be here, and it's great to have these type of discussions, particularly focused on AI in science, because this is actually the mission of our team. We started 3 years ago with the with the mission to create policy measures and funding that facilitates the integration of AI in sciences. I am a policy officer in AI and science team, and I'm going to talk to you from our perspective of DGRTD and AI in science. But of course, keep in mind that whatever I say fits into the global context of artificial intelligence in the Commission, that this global policy is being carried out by DG Connect, and you have heard the news about AI factories, gigafactories, the AI continent communication. So this is the global context in which our policy for AI, particularly targeted at science, fits in. So as I said, we started with the vision that integrating artificial intelligence in science can accelerate scientific discovery, facilitate the work of scientists, and increase the impact of science. And by doing this, we think that AI-enabled science can improve European competitiveness and, of course, contribute to addressing many societal challenges. And this is not just the way we think. Essentially, the Nobel Prize winners last year were for AI in science, and this view is shared by international organizations like OECD that says that the uses of artificial intelligence in science is probably the most valuable of all uses of artificial intelligence, and similar opinions have been shared by the CEOs of DeepMind, Meta, and OpenAI. In the US, Argonne National Lab has a special avenue for artificial intelligence in science. The UK Royal Society as well is working a lot on that. So we are not alone. The Commission is not doing a niche policy in a way. The policy objectives that we have, I can summarize them there broadly too. One is to accelerate the uptake of artificial intelligence by scientists, we hope to achieve that by strengthening their data too, their access to data and to computational resources, by identifying strategic R&I investments for the use of AI in science and supporting this with the proper funding. Also, the goal number 2 is to monitor and steer the impact of artificial intelligence on the scientific process, and that includes preserving the scientific integrity, promoting interdisciplinarity, preserving public trust, and of course the impact, monitoring the impact on researchers' careers. Now, when we started maybe 3 years ago, this was just a political narrative that we were trying to promote. But this year, many things changed because this narrative became part of the political priorities of the new Commission. So if you have a look at the political guidelines of the new Commission and the mission letter of the Commissioner for Research, you will see 2 key tasks that concern artificial intelligence, particularly in science. So one is the setting up of a so-called European AI Research Council, whose role is to pool resources similar to the approach taken by CERN. And the second big task is to develop a strategy to increase the uptake of artificial intelligence by European scientists. So these are the 2 big things, initiatives that we are currently working on alongside many other activities, but these are the 2 crucial ones for this mandate of the Commission. So I'm going to just highlight how we do our work on these 2. So the AI and science strategy is currently being prepared. We expect to have it published in September, and it will address some common challenges. It will propose an action plan, of course, with some flagship initiatives aiming to address some of the challenges that we face with access to data, computational resources, talent, funding, community building. Part of this strategy is the AI Research Council. Now, it has a new name because in the latest AI continent communication of the Commission, it took a more concrete shape, and this AI Research Council will be actually implemented as what you see here in the red box, a resource for AI science in Europe. And the objective of this resource for AI science in Europe is to pool and focus resources to priorities for AI science. And I have put AI in science in brackets because AI science covers not only the computer science aspect, but also the applications and the development of AI tools, particularly for science. Then a third important strand of our work is the work with EU and associated states. We organize learning opportunities for them and platforms to meet together, to align policy, to discuss funding agendas, align funding priorities, or do things at European level, like, for example, guidelines on the responsible use of generative AI in research. It was a product that was produced by us and this a group of member states and associated countries. And finally, another important key action is the investment agenda. Maybe many of you already know that the funding calls of Horizon Europe for 2025 have been pre-published actually, and yesterday we had the info day where I presented two calls that for the first time are particularly focused on AI in science. So one is for the development of foundation models for science, and the other is a kind of cooperation support activity that will pave the way to this future resource for AI science in Europe. We call it RAISE. This is the abbreviation. That's why you see here RAISE. And of course, we are also looking at what should be funded, what priorities should be funded for AI science in 26, 27, and beyond with the new framework program for the future. So this was very briefly what we do and the key actions we focus on. Should you like to stay in touch, join our mailing list for news. We don't spam people. We actually very rarely release information, but if you are interested to receive some updates, get in touch with us either through the email or by scanning this QR code to join our mailing list. So looking forward to the panel discussion. Hedi.
Thank you, Daniela. So as you said, questions will come later to dive more on this policy to support research and science. So for the attendees, we have a Q&R channel. So if you have questions for speakers, you can use this channel. Let's now hear from researchers. Our first speaker is Professor Ismail Benayed from ETS Montreal, where he holds a research chair on artificial intelligence on medical imaging. His interests are in deep learning, computer vision, optimization, and medical images. His research team also received several recent distinctions, such as Best Paper Award at the International Workshop on Foundation Models for General Medical AI in 2024, and the Best Paper Award at the Medical Imaging with Deep Learning Conference. Also, his team several times was top-ranked positions in internationally visible contests. So, Professor Benayed, the floor is yours. You are muted.
Okay, all good?
Perfect, thank you.
Thank you, Hedi, for the invitation and the rest of the team. Really pleased to talk here about maybe a little bit foundation models and some use in medical science. So I managed to make it non-technical presentation. I managed not to throw any question, which is kind of a challenge for in a talk. So So yeah, bit of a high level. Probably, you know, more already in the progress that has been made, you know, in the decades, from perception to imaging to content creation, and of course,
Ismail, there is some trouble with the mic. I don't know, maybe you can check your configuration.
okay, let me check. So there is some noise.
Yeah, like there is cutting when you speak.
Okay.
At least being like near the computer better, maybe.
Okay. So how is it now?
Is better.
It's better. Okay. So yeah, and bioinformatics and so on and so forth. So what I'll do is basically I'll try to maybe just 1 or 2 minutes about some history and how we went from very basic cognition for machines, maybe a few decades ago, to foundational model, which basically learn in a task-specific way, perform many tasks across many modalities of data. So I'll show you some examples. Again, I'll try to show some use cases in medical sciences. 2 agents are basically sequences of tasks, diverse tasks in a sense, and how we are getting basically to agents that are at doctoral level, PhD level, which is facilitating.
Sorry, Ismail, it's still not clear. Like, I mean, we cannot hear you very well.
Maybe Ismaila, can you turn off your camera? Maybe because I think it's a problem of connection. Maybe if you turn off the camera, it improves a little bit.
I'll try. Okay. So how is it now?
Let's try.
Is the sound better?
Same. Let's say same. So I don't know. Maybe what I can suggest, if you can get like an external mic, and in the meantime we switch with Salim and switch the presentation. It's work.
And then I would maybe disconnect and connect again. Okay.
Okay. Perfect.
Yeah.
Sorry for that. So in the meantime, we'll move to the next speaker and then back to Ismail later. The next speaker is Dr. Salim Belwatar, who is a specialist in the digitalization of materials and processes with in the Luxembourg Institute of Science and Technology. Salim research contributes to applications in aerospace, automotive, and biomedical engineering, with an emphasis on digital twin technologies and AI-driven modeling and design. Salim, the floor is yours, and glad to have you in the panel today.
Thank you so much, Hedi, for the invitation and also for the opportunity actually to talk to the audience. As you mentioned actually in the meeting, in the introduction, my talk essentially will be dedicated mainly to the application of AI in material science. And I will see this actually from the perspectives mainly actually how artificial intelligence is reshaping the field of material science and engineering in the global sense from my personal point of view. And the second aspect of the presentation I will show mainly is essentially to show the current state of the art essentially in the application of the AI in the field. And I will show more or less actually the main challenges we are facing as scientists and also the main, I would say, opportunities ahead in the field. I will also show some of the examples, we are from our research group, essentially we are doing, but from this example, actually, I will show mainly not only the example, but essentially the lesson learned as a research team, essentially from this example. And also I would say the work that somehow still needs to be done. I try just, I don't know why actually I cannot get it full screen. So, okay, I will do it this way. Can you see my screen correctly, actually?
Yeah, perfectly.
Yeah, okay, great. Then I want just to be sure, actually, that everything is okay. Then I will just introduce myself first, mainly. Essentially, my name is Salim, as mentioned, Salim Belwitar. I'm from Luxembourg Institute of Science and Technology. LIST is the biggest center in Luxembourg, essentially, and we are active in that field mainly in AI in different applications. The first essentially is linked to medical application environment, but also the development of AI as well. And of course, also AI for material science. As an RTU, I mainly essentially collaborate with industries, means actually we are trying essentially to go from TRL 3, 4, and actually up to see essentially what. This is why we are looking more on the impact and the application of the technology in the field. I'm sorry, I have just always actually because, okay, I before actually go into this, I want to show mainly I want actually to mention how the shift essentially we have right now in material science. And if you look, essentially, we are really, kind of, I would call it pivotal moment in the sense, we are in the past we have been working essentially in terms of paradigm, starting essentially by empirical science, and from the 15s essentially the progress in computational science. But today we are really moving on something actually, that associate both. And this is the connection between actually computational science, data-driven science is really where the impact, I think, will be the most important. Another aspect actually that pushed the application of all this, what we call machine learning or artificial intelligence or data-driven approach in material science is essentially two things. The first one is today the challenges are more complex. We are looking at the same time to sustainability, energy storage. We have a lot of problems actually with advanced manufacturing, but at the same time, we are looking mainly actually to get it faster and reliable. And this is the reason why actually we have really to look at different approaches than the one actually we have in the past. In parallel, if you look ahead and around, we are at the same time generating really massive, I would say, a massive data set. And we are at the same time exploring actually, increasing complex, situation and materials. This is what at the same time, we are, by using AI, we are more or less using this essentially as a tool that can help us mainly actually to make sense from this complexity. And this is where the AI enter in the picture, not to replace, as I mentioned here, scientific knowledge. It's really essentially to augment this and make sense of it. Okay, let's move to the next one. If we look first essentially about machine learning, artificial intelligence, we have to look at actually not as independent. In material science, we look at it as a workflow. And this workflow, it's somehow, it's linear, but at the same time circular. And it begins mainly in any way actually by data and material, and an objective. And this objective is essentially, it could be looking for, new materials or designing new materials. And this essentially is used mainly to create what we call the fingerprint, or sometimes we call it also, I would say, descriptors of this, material. And at the same time, the loop actually continues and the cycle continues, helping essentially to optimize and improve the design. And this, what we are looking for is to get it, much faster, but at the same time, much faster compared to the traditional methods. But at the same time, it supports us mainly essentially where the conventional approach or physical-based approach we have in the past mainly actually are not able to answer that challenge. And here actually we should just look to the artificial intelligence from different perspectives. And this is where the complexity comes in. Because behind the word machine learning or artificial intelligence, we have actually different, complexity, different approach. And this approach actually depends really on the objectives. And if we use models that, for instance, find patterns with in data without labels, this actually, we call it unsupervised learning. And this for tasks like, grouping materials or reducing data complexity. Other approach, for instance, could involve mainly the use of models that learn from labeled, data. And this is essentially, we call them supervised learning. And this essentially, I use it mainly to predict properties of new materials. And what is promising, in my opinion, mainly is the push recently to a new approach that involve agent. And this agent mainly learn through trial and error, and we call them reinforced learning. And these models actually can create new data, which we, at the same time, and this we call them generative models. All these models actually are used in different, application, from detecting, defects, from designing new materials, or from predicting how the material behave actually under new condition. And the understanding actually of this, different approach, how they apply mainly on a specific field of material science, this is essentially where the complexity comes in. But if you look also from deep learning, and I think the presentation from my colleague from Canada will essentially dedicated to this. And this aspect actually, essentially, if you take, an example of image-based model, and you would like actually to analyze microscopic images to classify material microstructure or structure, this actually deep learning approach will apply. This model are essentially based on graphs. Models that are based on graphs, for instance, are excellent, for instance, to describe atoms and their bonds. And these are crucial, essentially, when you would like to model, molecules or crystals. And we have also models that, process sequences of data. And this is essentially helpful and useful how to understand how material properties, could change over time. By saying this, essentially, I want to stress out the fact that the right model architecture is really important. And by choosing the right model architecture, we can actually at the same time tackle different types of problem more effectively. Whatever actually we are looking to interpret images that are coming essentially from microscopy or modeling atomic behavior or analyzing time-based processes, the architecture of the model and the selection of the right model is really important in this sense. This is why the expertise comes in. Sorry, I have to change manually the slides. I don't know why. And as I mentioned before, I think in my personal opinion, is the shift essentially to generative models is really completely bringing in new perspectives and new challenges in the material science. Because these generative models mainly actually have the possibility to learn from existing materials. They can also suggest completely new ones. It's like you think essentially that you are working and you have, an assistant which is really creative and have studied, millions and thousands of existing components. And now from this analysis, he is able actually to propose a new combination that might work. It doesn't mean it works, but that might work. And this proposal actually are not guessing randomly. They are using really pattern that has been learned, from the literature, from the data that exists. And these models actually can create completely a new digital representation of material, but at the same time, they can simulate how they might behave. And even they can also help us to focus on experiment on the most promising candidate. And this is, in my opinion, really a huge shift how we can explore in the future, essentially, the new material space. Here I will show just, essentially what we did in the past. I'm showing this example not actually to show what we are doing mainly at LIST, but I'm taking this as an example, to show mainly how we are moving essentially from traditional based simulation to model, complex behavior. If you take the example actually of the fuel cell, it started really, from the chemistry and the interaction, at very low scale. And there also, if you look at the microstructure, of the material in terms of geometry and microstructure, also this is really a key aspect essentially in the behavior of, of the fuel cell. But if you look actually to the fuel cell as a whole, this is at the macro scale. This is the complexity actually become much more, complex. If you want to explore that complexity using a kind of, physics-based, model, the complexity is really huge. And this is why we tried essentially to bypass this challenge and complexity by exploring alternatives. And this alternative is essentially to use machine learning. Essentially, this is a class actually of artificial intelligence. And what we develop essentially, we develop models that learn the relationship between the design parameter and the performances. And we were able essentially to predict much faster and without running full simulation. That means actually we have some parts of the model in the workflow that essentially we are using machine learning for it. And this make it, I would say, if I may say, much easier to explore the design option because it's essentially about this. But at the same time, we can tune the performances in real-time application of the fuel cell. Here, what you can see when I'm showing this slide to show merely the complexity. I'm talking essentially about input and output. And the input, actually, the complexity comes essentially from the call them variables, or we call them feature in this case. If you take the geometry, we have six features actually that describe the geometry. In the electrodes, we have 12 features actually to describe the electrodes. You can do the same thing actually for the electrolyte on the anode. And then we have the operating condition. Actually, we have 4 features. And this complexity in terms of the input, we have to link it essentially to the output. And the output, we are looking essentially to performances. And the performances, it could be the current density, the power, and the other, operating conditions that are important. What we did here, essentially, we tried essentially to use the machine learning, and I will show just some of the results in the next slide. We just tried essentially, for instance, to use this artificial intelligence to estimate, for instance, the polarization curve. And we have been very successful actually just using, very, I would say, lightweight model with only limited numbers of layers. This is the layers actually is the number of, in the neural network is the different layers we have essentially. And we have, almost 20 computing units in each of the networks. And at the end, we get really what we tested this on the simplest case, and we have a very high accurate prediction for the fuel cell performances. And it shows also that with the right data and the problem setup, even simple model can be very powerful. This is actually what the added value of this. But from this, actually, I will show you in my next slide, essentially, what we learned, essentially in terms of what is important in the workflow, in the approach. And we can see here essentially that machine learning, artificial intelligence is not used. It's not used only for the like a classification or pattern recognition. It's also really, used for accurate, I would say, scientific prediction. And what is important also you have to learn from this is the model is really lightweight. Lightweight means at the same time, look in terms of application, means actually it can really apply in real-time system. Means you can run the system and get information for essentially for a feedback control, or at the same time, it could be also used, for a rapid design optimization without running actually simulation that take days. I'm showing in the next example, I'm showing mainly essentially if we look beyond this complex application, we can also look to the use of artificial intelligence for polymer characterization and property prediction. And as I said before, essentially, it depends really on the model you are using. For instance, if we are looking to microstructure, means morphology in the polymer, then we have used actually CNNs. And this, to see the morphology. And in this case, actually, what we use is essentially image-based deep learning models that classify the structure like lamella or spherical morphology, and this essentially using the scattering pattern or the microscopy images. And the approach, what is important in the approach is the possibility to automate the approach. Means at the end, we can I would bypass all the manual process and make it faster and at the same time more reproducible. And if you look from other perspectives, you can see that in terms of PSP, microstructure property relationship, you can link the microstructure to the material properties, and this will enable easily actually the prediction of polymer performances based on this. But what we are essentially using much, essentially the machine learning on our side is mainly on the composite, material and structure. This is why we are really, very positive in the sense we see that artificial intelligence is really showing great promises. The reason for that is the complexity in composites. Most of the time, you have complex microstructure with different interfaces, and this sometimes actually it's very difficult mainly to analyze these properties using simulation or experiment. And even sometimes, if you go for experiment, you need really require detailed simulation. What we do essentially here, what we are developing as an approach, at least we are separating actually the two parts. Like modules, actually, we apply a model. We call it actually, this is a model for data science or data science module. And this is essentially goes for the application of statistical approach and machine learning, essentially to handle not only the data, but what is important essentially is to handle the variability and to see that the samples and we are studying represent somehow actually the full range of behavior. Then we return back to the simulation on this example using computational models, and this will help us mainly essentially to predict effective properties. But what is important here in this case, what we do essentially, we store the data that generated either experimentally and simulation and in a database. And this database actually we separate essentially from the different scales. We have actually this data that will be used mainly actually for further development within the approach. I want to also to highlight, one of the work of my colleague. We think really with my PhD essentially who is developing, who also made also this slide, and he's working essentially on the promises that hydrogen in terms of the photoelectrochemical reaction is for the hydrogen application. And we, at least we think that this, is one of the promising, I would say, clean energy technology for the future. And the issue we have here is if you would like actually to design a new photocatalyst, this is incredibly difficult. This is mainly due to the vast number of chemical components. And right now, only a small fraction of these chemical spaces is being explored. This is why we turned actually to the machine learning to screen this enormous space much faster. And the approach essentially is that we keep the artificial intelligence suggest, the promising molecules, and also to predict how these molecules will behave. And even we're asking actually these tools to explain us somehow actually why some candidates are actually work better than others. In other words, artificial intelligence here is really helping us to understand the underlying mechanism, such as how light is absorbed or converted in the chemical energy. But at the same time, it helps us also to design better catalysts actually from the ground up. And what we are doing essentially, we are really moving completely, in terms of approach. On the upper of my slide, you see the conventional approach essentially that has been used even based on machine learning, how we started essentially from data collection. We go actually to the featurization of that data spaces, and then we go to training model, and then from that actually we evaluate the model and we explore, and then we see essentially if this works or not. We are moving essentially to a completely different approach because we think this is not the best way to do, and this is why we are using essentially generative AI essentially to this. And what we do essentially, we try from here that the workflow that you see on the bottom mainly allow us to go really from raw data to potential discoveries in much less time. And this is, that, traditional methods could take. And, and because the system actually learned, from each new results, it gets even better with time. And this is essentially what we call somehow the guided approach, guide, learn, and propose. And this is essentially what we are really doing in this case. By showing this example, I will not talk to this. There is a talk will be dedicated actually to agent workflows, because what we do essentially, we implement an agent workflow within actually the whole approach, essentially dedicated to looking mainly essentially to this, possibilities in terms of data, but also in terms of knowledge.
Sorry.
Yeah,
please, if you can summarize and wrap up.
Yeah, actually, I will summarize. Thank you, Hedi. Sorry, I will summarize very fast. 1 minute. I will show essentially from this analysis what we learned. We learned essentially that the data is really important, and the data is really represent a critical impact actually on ML effectiveness, and at the same time is 80% of the effort. This is why pre-processing and the quality control of the data is really important. The other aspect we learned essentially, there is a really poor integration with actually if we go for multi-model and multi-scale data. And there is also the aspect linked to the low interpretability actually of the results and the lack of benchmark. And at the same time, essentially, there is a generation challenge, because when we go to machine learning, artificial intelligence, we are always dealing with a specific problem. What we learned mainly actually from the multi-scale modeling is essentially the multi-scale integration. If we go essentially for a specific problem at one scale and you want actually to connect to the other scale, no, there is no pipeline that propagate actually that, that link the scales, but propagate also, uncertainties from microstructure to performances. We need also generalization and extrapolation, and also the integration of legacy system, because when you propose a new system based on machine learning or artificial intelligence, it should go essentially for what exists. And this is also, I would say, lacking in the approach we have now. And just to summarize, actually, in our opinion, essentially, what are the barriers, in terms of adoption and implementation? The first one, we call it actually computational scalability. And the other one is the hardware constraint, essentially, because it's really, I would say GPU demanding. And we need also specialized resources. This is at the same time one of the barriers. The second aspect is linked actually to security and robustness, when also we have to make an effort, essentially, how the data is shared, and at the same time, how it's secured in the robust way. Also, this is what we think essentially at the next step in terms of challenges. We need in the future actually to work more on the collaborative data curation, active data collection, and we need also a lot of effort in terms of standardization, and the work also at the same time, interestfully means actually uncertainty aware learning, and also how we can generate synthetic data. And this finish, my slide, and thank you so much. And I'm sorry if I took much more time, actually, Hedi.
Thank you, Salim. Thank you for the presentation and those clarifications and ways of development of AI as a booster on material science. So if there is questions, please go through the Q&R channel. Salim will be there to answer questions, and then also we'll have the possibility to discuss more during the panel. So let's back to Ismail. So I hope that it works now. Ismail, please go ahead.
So do you hear me better?
Perfectly now.
Perfect. Okay. Okay, so sorry for that. Yeah, it's been like a decade of deep learning with mind-blowing actually progress. I'm not teaching you anything new about this in area of autonomous systems and in medical science, in medical imaging, biology, bioinformatics, drug discovery, genomics, and so on and so forth. And so what I will do, I will go very quickly, 2-3 minutes, about some history of deep learning and how we went from very basic cognitive tasks like image classification to foundation models. So everybody's talking about foundation models. So I'll try to show you what does it mean. It's basically models that could be agnostic to tasks, could tackle a huge amount of tasks, to agents, which is basically also a sequence of tasks. And I'll try to show some example at the end from our research in medical imaging, where we are getting to doctoral level, basically, or PhD student level predictions that we make from images, and some examples also for deep learning in medical sciences, and how the impact is the potential impact for scientific discovery, drawing insights from large amount of data which human cannot do on one side, to uncover biomarkers and aspects like this from complex data, but also doing PhD level tasks like literature review and reasoning, and facilitating the research tasks so that human could focus on creative tasks. And this is actually orthogonal to medical sciences. It's all sciences. So basically, what I see is the impact that internet made on science, in the sense that it facilitated the literature research. Now the impact of AI is going to be even more exponential, because it facilitates all the tedious tasks of a researcher, basically, including experimentations and so on and so forth. So yeah, sky is the limit of what's going on. Now I don't understand how we are still talking about hype. There is no hype. It's an actual revolution, and we are just at the beginning of it. And data keep growing. Data centers keep growing exponentially. And what we learned in the last decade or 2 decades is that data is what it is. There were algorithmic breakthroughs for sure, mostly engineering feats to handle and scale for data and compute, but it's data, and with the current growth, yeah, we are just at the beginning, I believe. So just this is, I lived through this because I was a PhD student in computer vision. Just I will take a minute for some of you who do not know this. And at that time, in the years 2005, 2020 years ago, basically, and computer vision and very basic cognitive tasks were actually, challenging. Very challenging for machines and for algorithms. For example, you want to give a class to an image. This is an image of a cat or of a dog. When you think about it, it's a very basic cognitive image. We want machine more than that, doing more than that, actually, like looking at an image and describing it, for instance, or robots doing this. But and even at that level, we were very, like, we make an error out of in 3 images. In very basic data sets where we have only 100 classes. That's the ImageNet challenge, the very famous ImageNet challenge. And what happened is in 2012, like, this is what restarted all this neural network revolution. Basically, it was a very basic computer vision task where Jeff Hinton team, the Nobel Prize, I mean, the rest is history, but from his team, it was Alex Krzyzewski, a PhD student, who basically ran some neural networks from the 90s, and had this kind of jump in the error by 10%. So to put this in context, like, we were going to computer vision conferences at that time and seeing just like fraction of improvement, like we are in a crisis, making error in those basic cognitive tasks. And then there was this jump of 10%, and everybody came back to neural network. And since then, the ImageNet challenge, 1.5 million images, 1,000 classes, was almost solved by 2016 by scaling and increasing the deep networks and the number of parameters. Even at that time, it was millions of parameters. And all of this is essentially order of magnitudes more data and compute, like I said. So the technology and the idea existed back even in the 90s and even decades before of neural networks. So this brings me to something. When you think about this, and you put it in context, and like people like me who saw this complete shift back a decade ago, and you think it's actually even a very toy task, like given a class, it's a dog or a class for an image. It's very, very toy, right? You don't even have many use cases of it. Actually, you want machines to, an image is tons of concepts. Like, for example, this image, you have a person, you know, you have a photographer, you have camera, you could talk about the street, restaurants, the whole thing. So you want, it's better described with complex large language, and you have many concepts. So the world is not just 1,000 concepts of ImageNet, and we were very far away from this back in 2012 indeed. And then the next 10 years after 22, and language is the best way to encode like infinite amount of concepts. And then comes ChatGPT 22, 10 years after. And the main difference is compute and parameters. So we were reaching billions of parameters in those deep neural networks. And now we are reaching trillions of parameters of these perhaps multimodal models, where you have images, you have language, you have many things that a model learn from. For example, it came to computer vision with those vision language models, where models like Clip, again from OpenAI, were trained on 400 million pairs of image and text collected over the internet without even supervision. And then now we are scaling more and more. So why I'm saying this is just to show you some examples. So we basically train from, imagine you train from images and the text descriptions at very huge scale. So let me show you, and this is propagating to medical imaging, for instance, which is our area. So we had a few works in this, and this is also making significant development in medical imaging. Why I'm talking about this? Because this is a very good example where, in fact, we are actually going into an area where we went from very basic cognitive tasks to predictions that are doctoral level. Like it could be a histopathologist, it could be an ophthalmologist or a radiologist, predictions and text descriptions of images, and to PhD student also level of tasks. So, so this is an example from our team where we trained a vision language model for retinal images. So the task here is to make a diagnosis from fundus images of the retina, and not just a simple class, but also in this case, for example, moderate diabetic retinopathy, but also saying why, you know, what are the biomarkers that led to this decision. So it's basically doing the prediction of an ophthalmologist in some sense. So going back to Jeff Hinton, prediction maybe a decade ago, I was very skeptical, you know, that machine will be doing the job of medical doctors. I'm not saying we are there yet. There are many other reasons that we could not do that, ethical and legal and so on and so forth. But we are very close to predictions that look like, it's not cognitive tasks, it's not simple memory tasks, it's expert level task, basically, and scientific tasks. So this is what you could see here. And of course, the impact on society could be huge. For example, here you could think, okay, oh, well, from the panic point of view, oh, this is gonna remove the job of ophthalmologists. Well, no, because we have a lack of ophthalmologists, and people sometimes, at least in Canada or in the US, spend 6 months to see an ophthalmologist, and by then they could become blind actually from these abnormality. Actually, the numbers are scary. So it has actually substantial benefit. So this is not science at this point. This is diagnostic and doing the job of an ophthalmologist. But let me show you examples of where it gets really to kind of superhuman cognition, where you could extract measures from images that are super complex that a human could not extract, which are at the pixel level, basically. And then I will get some example from some of our works of how this could actually enable to discover biomarkers and to push the boundaries of health-related research from medical imaging. So I'll give quite some few specific examples. So of course, foundational models are not just for vision and language, but for complex tasks, dense tasks, for example, trying to give a meaning to every pixel. Think about an image like this. For obvious reason, for robots, for autonomous system, you want to give every pixel an image a meaning, like a car, tree, and so on and so forth. There are foundational models for this, like the SAM model from Meta, for instance, with 1 billion objects, 11 million images that cover pretty much a model of the world. And you could think of this task as superhuman cognition. I mean, we people don't perceive or give a meaning for every pixel in the image. So why this is interesting? So think about this in medical imaging. So there is a whole area in medical imaging. This is some work from our team about building foundational models, for instance, like deep foundational models for segmenting organs in CT and MRI images, like what you see here. So you give a meaning for each pixel, for example, kidney, liver, so on and so forth, in this case of organs, or tumors here, or brain lesions here, or even vessels in the retina, complex geometric structures of the vessel. So you could extract this. Of course, human cannot do this. But what is interesting here is that those geometric, you could extract from these structures, like vessels here, for instance, some kind of complex geometrics measures, for example, like tortuosity, which is known to clinically correlate with cardiovascular diseases, actually. So so basically, a human by the naked eye could not extract this information, or could not digest this amount of information. AI could do, segmentation foundation models could do, and then maybe we could discover complex biomarkers that correlate to disease. So this is where the scientific aspect get really interesting. In fact, I mean, instead of manually trying to get to this data, so we cannot do this by a human in a sense. So this is kind of superhuman processes that in a sense could enable us to discover biomarkers of complex diseases. Okay, this is an example, a nice example, also a segmentation work from our team, where basically you could see here the 3D subcortical structures of the brain. So it seems like volumetric, complex volumetric measures. Of course, a human cannot do this, or if a human has to do this, it will take hours and days to do this in 3D, and then to try to compute manually some measures. But like machine learning models could perhaps correlate very complex volumetric measures to complex disease like Parkinson or Alzheimer's or things like this. So a very cool thing also that made the progress steady and very fast is that there is this culture of ecosystem where everybody publish these works. For example, this paper, we publish it, but also we put the code online for free on GitHub, and this is a community effort. And then we were, for example, contacted by the Canadian Neonatal Brain Research Association, who wanted to use it for research purposes, actually, in healthcare, because it facilitates completely their job to extract complex geometric measures of the brain and maybe discover biomarkers in some sense. So this is a quite cool example, in my opinion, for AI in medical sciences. So there are maybe, I will just mention two other examples that are maybe where I think I believe AI algorithm and deep learning will be pushing to completely new frontiers. The first is drug discovery. We started also in our team, in our large team. It's a computer vision and machine learning team. We are technical people in a sense, but we started also looking into drug discovery problem, where essentially the algorithm like go through a huge amount of data to try to find drug candidates. So the process used to be done manually by experts to find drug candidates, and it's extremely expensive. Many drug candidates fail in the clinical trial, so it costs a lot of money, and there is a huge potential for algorithms to discover appropriate drug candidates, or the so-called also drug repurposing, where we use data, large amount of data of an existing drug with its disease target to potentially find similar molecules that address new diseases, the so-called drug repurposing. And also personalized medicine, where we use, for example, the medical history of the patient or genetic profile of a person to find targeted therapy and so on and so forth. So the frontiers on that side and the potential is just huge. It goes the same for genomics, where we could, algorithms could analyze huge sequences, genetic sequences, to identify disease markers and sense. And again, personalized medicine will be where treatment could be tailored to individual profile would be another frontiers in a sense. So these are some numbers I found which are actually mind-blowing. So when you think about the potential to decrease the cost beyond the society effect, because you would have drugs, for example, faster to the patients, but also the cost, it's order of magnitude in reducing the cost. And let me let's just finalize by what I see now. Again, I was skeptical maybe 5 years ago about getting to robots that have this kind of autonomy, or autonomous cars that have this level of autonomy. We are still not there, but I thought it will take us 2 decades, maybe back 5 or 6 years ago. I changed my mind, and it seems like data and the scaling is doing it basically, and it's not stopping; it's increasing exponentially. And then we are getting, and this is for science also. This is a vertical. It's not necessarily medical sciences, but like we're seeing reasoning models that could understand and interpret an ever-growing scientific literature, and like extract some trends from it, facilitate literature review. You basically could make literature review with agent and some meta-analysis. Agent could conduct experiments with high precision and consistency in areas such as biology, for instance, at PhD level, right? Automate data collections, processing, and even coding, for example, for computer scientists. So all these tasks related to doing research beyond finding documents in the internet, like the internet facilitated. Before internet, researchers have to go to libraries and try to find, and it takes them a huge amount of time to find information in the literature. So internet was a huge deal. But think about an exponential gap now, where all the tedious tasks that a researcher has to do, from data collection, coding, extracting useful information from the literature, all this will be reduced significantly, so that the human will focus on the creative aspect. So sky is the limit. Just an example. Again, we are computer scientists, we are technical guys. So I was asking an agent, Grok, a reasoning model, about one technical paper of us that was published at CVPR last year, which is quite technical. Like, there is optimization algorithms. There are quite technical aspects that are involved. It's a vision language paper on vision language adaptation, or on the adaptation of vision language model. And I asked Grok, okay, can you give me the main takeaways, technical takeaways of the paper, and just for fun, and the response actually kind of quite impressive for me. That's a PhD level, good PhD students first year, or a good master students summarizing information, getting to the main technical aspects. And probably you've heard also that excellent model by OpenAI or other are getting good grades in tough math exams at Stanford and things like this. So I'm not saying that algorithms will get the Fields Medal in mathematics, but it's getting to a level where, again, it's not memory tasks or repetitive tasks or basic cognitive tasks, but we are getting to tasks that resemble professor tasks, PhD level student tasks, medical doctor tasks, and yeah, so
Great.
that's it.
Great. Thank you, Ismail, for this impressive presentation and a very nice example that allowing us to dive through what AI can bring to us in terms of improving our quality life, our health, and make life easier for also researchers. And this allow me to move to the next presentation about AI agents and one of the examples of AI research assistants. The presentation will be made by Victor Botev, CTO and co-founder of Iris AI. Iris AI is one of the EIC awarded companies. Let's say Victor and his team doing is impressive, quite impressive, to provide assistance to researchers to make their state of the art, their research analysis and so on. So Victor, the floor is yours. Please go ahead. I think there is a problem. Victor is disconnected. What's happened? I just was seeing him. All right, so let's move to the next speaker and try to connect Victor again. Yeah, he's texting me. Okay. Stefania, could you please move Victor to the speakers because he cannot unmute or share his screen.
Join as participants. Okay.
Yes.
Just a moment. I have to find it in the list. Okay. Okay, I authorize to use the microphone and
hello.
Hello.
Yes, we hear you, and I activate also your camera. Please check if it works. Okay, now you are speaker. Victor, can you hear us?
Yeah, we are seeing the screen. It's coming.
Okay.
Yeah. Can you hear me?
Yes, perfectly.
Yes. And we see your screen also.
Yes, I unfortunately I cannot turn on the camera.
Okay.
It doesn't get the permissions, but I hope it will be enough with the screen. You can hear me well, right?
Yes, we hear you, and we see your presentation at the moment.
Awesome. All right. Yeah, first of all, I want to say that there were very interesting presentations before, and I definitely agree with the last speaker about the pace of development. I will continue with the presentation more detailed about AI agents and some more use cases that are used in science and that we at Iris AI provide to clients. Yeah, Iris AI have been around for about a decade, and currently we are serving mainly companies working at the material science sector, mainly their R&D departments and several research groups that work on material science. And I totally can agree with the statement that the difference with the new models, new machine learning models and generative AI models is significant. We see that new materials can actually emerge and be tested more or less 8 to 10 times faster than what we have seen before. So yeah, one of the things that I want to say here is that generative AI is currently the main trend in terms of using reasoning model to digest information and use it for research purposes. But one of the main issues when it comes to generative AI models and what prevents it from being used even earlier, because they are around for maybe about 5 years, ChatGPT maybe about 2.5. But they were not very much utilized in research because of a few main issues. And the major one has been the fact that they hallucinate. But not only that they hallucinate, but the fact that they do it so well that it's really difficult to spot the error, which I mean, even sometimes takes more time to find the error than if you actually do the work manually. At least that was what was happening at the beginning. But things kind of changed in the last 2.5 years. A lot of research has been done in how to more or less the way we call it tame the models. So basically reduce the amount of there are 3 approaches that we take at Iris AI. First one is smart engineering, which essentially means to provide the right context to the model in order for it to answer the question. You probably have heard that there are lots of generative AI models that have large context. You can provide millions of tokens and stuff like that. It is true that, but also there is this old saying like garbage in, garbage out. So providing a lot of noise inside the context that we give to the model can also confuse it and not give us the end result that we want. And especially in research, that's quite important. So it's really key that we provide the right context, that we also provide some structure that kind of guides the model toward what we really want it to get. And there are lots of engineering techniques out there. There's not really much reinventing the wheel here. I mean, there are several search techniques, for example, for finding the right information. There are lots of indexing techniques as well. We just have to use them to extract the right context, and then providing it to the model helps a lot in its reasoning capabilities. The second approach that helps a lot here is also a diegetic approach. What I mean here is that usually when you use a model, let's say like ChatGPT or another large language model, you send a question and then you get an answer, and that's more or less a one-shot interaction. But if you use several viewpoints of this model, so you can create several agents, you actually can make the models spot their errors and finally refine the answers. I would say a little bit more about this and show one interesting diagram here. And the third approach is it's really important to measure stuff. When the LLMs came out, we kind of faced head on one of the big issues of measuring generated text, which is essentially that this is a really hard problem. We don't have good metrics for actually measuring generated text against ground truth, especially if that text is paraphrased differently. Then the task actually becomes really hard. Still, there are several measures that are available today, and maybe an ensemble of that can give us really good indications of how the model behaves. And that also can give us some clues if the model is hallucinating as well. A few metrics that I mentioned here is readability. So that's basically if the model is producing good language structures. That's especially important in multi-language results, because in English the models are really good. But if you switch to other languages, especially low resource ones, this metric can drop down a bit. Meaning relevancy, to what extent the answer actually is relevant to the question. We're talking here about semantic metrics. And the final metric, which is actually even more important than the rest, is has the model actually followed the instruction and used the context that you provided. Now, moving a little bit further, so that is kind of a typical pipeline of basically converting a raw information into some systematic hypothesis in the research world. At least that's how we mapped it a little bit at IRIS. So you start first with some data sources. You have research articles, patents. You might have some internal documentation, like reports, memos, presentations, which could be of various content types. You might have time series data as well. All of these then goes into some sort of data processing. There are lots of data science pipelines that have been developed, for example, in our case in material science, but I'm pretty sure that this is also valid for other areas of science. And after this is kind of unified in one way or another, people are using various high-end features in order to kind of digest this information. Could be diagrams, 3D models. It could be any sort of summarization of all this information. Could be table data and all sorts of things. And not only that, but we also, in many cases, want to kind of monitor what new has come. So we don't want to do this exercise in each and every project, more or less, but we want to some extent, structure it so that if something new comes in, we only add the new data and see how it changes. And finally, there are lots of kind of tools, including our IRIS RSpace tool, that can present this kind of data at the end to the data scientists. This was more or less the pipeline maybe before last year, when the agents become like a big part of the software development world. Then things changed a little bit. So here is one example of what I started telling about the agents, that, yeah, basically the common or like the traditional approach of interacting with LLMs is we sent a prompt or a query. Then it was to some extent processed by the LLM and then generates the report or the response. But what has changed more or less is that now we have the possibility to build different agentic workflows. In many cases, this can increase the quality of the results. What I mean when I talk about agents, about different points of view, for example, in this chart here, we can see that we receive a query from the user, and usually we put it into some sort of system prompt template and send it to the model. But actually, there could be an agent that checks that query, and based on previous interaction or based on some context about the project in which this query is embedded, it can rewrite it so that it's better understood by the next agent. So that's, for example, one task that an agent could take. Another task could be a classification task, just to understand, do I need more data, like a retrieval, or not? Can I answer the question right away or not? Then there could be other stuff like which retrieval would be better. Like, should I go and take some time series data right now, or should I go into a vector database or a graph database or whatever? And after that, I can have also we can have also in these workflows like a quality assurance agent that checks how good the quality is. Although one must say, okay, so if these agents actually have the same underlying model, why is this better than just getting the one-shot answer? Well, the thing is that when we provide the prompt, we actually guide the model towards the next thing to generate. And here, by giving a totally different perspective, I mean, in one case, the model should be a quality assurance person. In the other one, it should be just a rewriter of the query. In the other one, to be the actual processor of the query and so forth. We're giving a particular concise tasks which guide the model generating a result about this specific task. And in this way, we create kind of different points of view towards the same question, which when unified change things. In our view, with one-shot questions, especially for specific scientific domain, we might get like 70% accuracy or about that. But when you put an agentic workflow, things go 20% higher at least. Here is a bit more about agents and what we think about them in the case of in Iris. So we have they have to be specialized. The prompts need to be very targeted towards the specific task that the agent should be solving. In many cases, we want them to be small, meaning that the models that actually solve the task should be sized towards the tasks they're solving. I mean, if it's a classification task, we don't want to use like 400 billion models, but 1 billion model, let's say. We might need to distill this knowledge. There is a lot available right now in the research world about distillation and how you can use this teacher-student approach to have a bigger model teach a smaller model to solve a concrete task. The small model loses all its other capabilities, so you cannot expect it to be general anymore, but it becomes as good as the big model on the concrete task, and that reduces the cost significantly. And finally, when it comes to evaluating these agents, one of the approaches is also to use larger models as judges of how good they are. And this allows us to guarantee the quality of the different agents. This is the same kind of graph, again, illustrating that each and every task that we have here is very specific and very targeted, which allows the models to excel much more and produce the correct responses. Yeah, so as I mentioned, it's really important also sometimes to choose the right model because some models are better in processing structured data, some models are better in reasoning, and so forth. And everyone that wants to implement anything related to GenAI should be using metrics to measure how good the models are performing, and it's really important to measure them in the use cases that you're working on. So we have developed an evaluation framework with 23 different metrics that is able to tell us that. A few things additional to the metrics and measuring the models just on the accuracy is also to consider, especially if you're working in environments where ethics is important, transparency, security, data protection, to also ensure that you kind of build things from the start thinking about these things. Ensuring data protection and security later is much more costly and difficult than if you start from the beginning. A few of these components, I mean, we addressed them, for example, making sure that the models transparently are following the use cases we want. We ensure by having these evaluation frameworks. When it comes to guardrails, adding additional agent that actually tries to rephrase the answers based on particular rules for disinformation or pseudoscience detection helps a lot as well. Biases is something that we have seen to kind of ruin the reputation of certain models in the past. And so providing the right data when you do in-context learning or any sort of training is also really important. And finally, when we build tools, we always try to make sure that there is a possibility for people that are less included in our society to also participate. We actually have a few examples in our Sofia office of people that have tried our services using accessibility features like speech to text and so forth with particular devices. I think it's really important to make sure that all people are included when we develop these AI agents, and it's not really that costly. I mean, adding an agent that does text to speech today is just a fraction of the whole agentic workflow. Here are some of the use cases that we cover at IRIS. Like one of the things that we started was reviewing scientific literature, summarizing what new has come out in a particular project or problem. That's how we started. Then there are a few other use cases that evolved with the partners we worked in, like post-market surveillance, essentially making sure that you're on top of what people are saying about your product or your device. Patent research and innovation tracking, so monitoring what is the intellectual property environment in which you operate, and helping you more quickly understand where you can actually patent new technology or where you need to figure out different ways to acquire it so that you can continue your experiments. And the final one is like more general on AI-powered data management. We have developed several retrieval strategies which we attach to agents. So essentially, you have the model that is using one index, let's say an SQL database, or like a full text indexing service like Elasticsearch, for example, and so forth. So we have more than 10 specialized agents on that, which help several organizations actually structure the data and provide the right context to the ends. So yeah, this is more or less what I have today. There are a lot. I mean, the topic of the agents is actually quite vast, so it can go in many directions. So I try to be more on the overview. But yeah, if there are any questions, I'm also happy to answer as well.
Thank you, Victor, for the presentation. And as I said, the Q&R channel is open, so you can ask questions to Victor. Now let's move from the technical aspects, from researchers and from startup perspectives to the business perspective, to the investment, the ecosystem, and the strategy and opportunities behind AI in science with our next speaker, Eden, who is a deep tech ecosystem architect and also investment strategist. She serves as expert evaluator for the EIC, and also she is also author of a weekly newsletter called Invest Deep Tech. So Eden, the floor is yours.
Thank you very much. So thank you very much, everyone, to having me here and to make this webinar possible. So let me share you my presentation. And actually, before I dive into today's AI opportunity, I'd like to introduce a little bit myself. I'm Eden Janashvili. I'm a deep tech ecosystem architect and investment strategist. I have helped secure over 8 million euros for space, healthcare, mobility, and AI innovations. I serve as an EIC accelerator jury expert with more than 5 years evaluating H2020 and Horizon Europe projects. I have also judged the Cartier Women's Initiative and been an ambassador for Hello Tomorrow. And besides of all this, I mentor startups at different European universities where I also teach innovation and entrepreneurship. And today I'm here to explore with you how Europe can actually lead this AI science race. So What if I told you that Europe could win a 2.7 trillion euro race? So last year, Europe invested 43 billion euros in AI, but the US invested almost 300 billion euros. And together with China, they control 80% of all AI funding. The US is actually charging ahead with breakthroughs with ChatGPT, while actually China is holding 70% of global AI patents. And actually, it's not only just them. We have Israel now that is home to over 200 AI startups, the UAE, which has committed 1.5 billion euros to AI projects, and we also have India, which is actually scaling its biotech AI hub with 2 billion euros in new investments. But Europe has still its moment. So let's take the example of Quinta do Vale, which is a Portuguese vineyard that used AI to boost grape yields by 20%, which added them 2 million euros in value. And that's the type of European impact we can make. And the great part of it, or the speed part of it, is that we have 18 months to reduce this funding gap, thanks to the new AI Act that will take effect this August. But a question here is, how do we actually seize this moment and lead this race? So we have some key advantages that the US, China, and the rest of the global hubs cannot match. And these are three main points. So the first one is the AI Act that will take place in August, which actually will ensure that our AI will be the most trusted and will create a 1 billion euro market by 2027. We also have over 15 leading labs like CERN, Sheridan EMBL, Max Planck Institute, and ETH Zurich, which are actually holding a quarter of the world's AI patents. And what we are seeing lately is that we have small cities hubs like Lisbon, Warsaw, and Grenoble that are coming in at about 30% lower startup cost than other European hubs. And what does actually this mean? So it means that we have more runway, we burn less, and we have higher return on investment. I like to share with you an example. It's Kemia. It's a French startup that has secured a 7.4 million euros last month from France 2023 grant program. And actually, they are using its AI platform to cut drug discovery time from about 5 to 6 years to under 2 years, which is actually a roughly 60% reduction. So these actually are the kind of European innovation that will put us apart from the global hubs. But as every great story, we also have challenges. And what's going to slow us down in this race, and what can we do? So first, we have this regulatory burden. So the AI Act, many startups are afraid that it will slow them down. But actually, with the EIC 112 million euros test zones, the European startups have a faster lane to actually have the support to meet the compliance and navigate all the regulations. There is an example of a German startup called Deploy, which raised 9 million euros using these test zones. And additional to all this, what we can also use is regulatory sandboxes that can offer startups flexible space to test their AI solutions while meeting also compliances. And we can also use workshops and clear regulatory guidance that can also help startups better understand and comply with the new rules. Then we have the funding gap. So the US spent almost 300 billion euros on AI last year, while we only spent 43 billion euros. But what we are actually seeing is that with Horizon Europe's 500 million euros in grants, this can help us close that funding gap globally. And we also need to use public-private deals that actually incentivize VCs and angel investors to back AI startups across Europe. Like, for instance, we can use like tax breaks or co-investment funds. Then there is another way that we can palliate this is to increase actually the size and availability of AI-specific funding innovation, like through the European Investment Bank, or even national and regional grants, like we have in Germany, France, and Spain, that are actually helping local AI startups grow. We are also seeing a talent gap that is taking 30% of our talent is going from our AI expert that is going to America, and we must bring them back. So how? We need to implement these tax breaks and initiatives like the EIC's €1 billion talent programs, or even setting up AI talent exchange programs and offering also AI training and education programs in university. So that way we can actually ensure that we have enough skilled workers in the future. Then there is the infrastructure limits, and we can say here that we are behind with only 80% of global data center capacity, while the US is actually holding around 60% and China is accounting for about 20% of those. But with the new implementation of Europe, with the European Chips Act, this is helping us catch up by boosting this Europe's semiconductor production, and it's providing the infrastructure that AI startups are actually need to grow. We also could use the public-private partnerships that can help build more data centers across Europe, and with government subsidies encouraging those private investments, of course. And we can also offer access to global cloud providers like Amazon Web Services, Microsoft Azure, or Google Cloud, which will help startups scale quickly using existing infrastructure. Then we have one of the points that you mentioned during this the previous presentations, which are the ethical concerns. And the ethical concerns around AI could actually damage our trust. But we have companies like Mistral AI that are leading the way with responsible AI practices. And they are following these models that can build trust and ensure that AI can benefit everyone. There's another solution we can actually use, which is to establish AI ethics guidelines that all startups must follow, promoting fairness, transparency, and accountability. And additionally, we could use the creation of independent ethical review boards for AI companies, which can help actually ensure compliance with ethical standards and also increase the trust among users. And finally, also offering AI ethics training for developers and AI professionals that can also help build more responsible systems from the start. There is one big hurdle, and this is about AI commercialization. And this is basically to turn academic AI research into successful businesses. And many founders today face challenges with IP issues, tech transfer, and the lack of commercial expertise. And what we could actually do to palliate those is to use the EIC Business Acceleration Services for mentoring and market access. We could also use and provide IP management and tech transfer support for patenting, licensing, and IP protection. We can also foster university-industry collaborations between academia and industry to actually help bridge the gap between research and commercial application. We can actually also launch specialized accelerators focused on converting academic AI research into AI business, providing access to funding, network, and business development resources. And last, we can also use to establish dedicated seed funding programs to specifically for academic spin-offs to actually provide capital that is required to move from research to commercialization and actually overcome all these financial barriers early on and speed up the access to the market. But now, what are the best opportunities that we can have for 2025 and beyond? So let's break them down. There are two parts. One is the short-term impact that we can have. The other one is the long-term that we can see. So in the short term, we are seeing that biotech AI is expected to reach 5 billion euros by 2027. That means a 5 to 7 times returns. There is AI that is transforming drug discovery, clinical trials, and personalized medicine. And they are speeding up the development and they are reducing the costs. There is an example of from Budapest, from a startup called Turbine. They are using AI to reduce cancer drug discovery costs by 30%. They are backed by a 20 million euro investment from Merck, and they are likely using a licensing model where their AI-driven tools are licensed to pharma companies to help them speed up this drug discovery. Then we have climate AI, which is growing fast, and they are expected to reach 2 billion euros by 2027. And this sector is driving sustainability efforts in carbon management, recycling, and energy optimization. Great Parrot is an example from a UK startup. They are improving recycling rates by 20%, and they are tapping into the 4 trillion green market. They are likely using a SaaS model, offering their AI-powered services to the recycling and waste management industries through subscriptions. Then we have cybersecurity AI, which is expected to reach 2.5 billion euros by 2027. An example of this is a Spanish venture called S21Sec. They are using AI to detect and mitigate cyber threats in real time, which reduces the security breaches by up to 90%. They are delivering their services via tiered SaaS subscription model, meaning basic, standard, and premium, for ongoing protection. And then we have AI in healthcare, which is actually expected to reach 8 billion euros by 2027, and they are looking to improve disease diagnosis, patient outcomes, and hospital operations. There is an example, again, a Spanish venture, which is called Cuventus. They are using their AI to optimize hospital operations, improving patient flow by 20%, and they are reducing wait times by 15%. They are offering a per bed SaaS subscription with the outcome-based pricing tied to the efficiency gains. And this is for the short-term impact. If we're going to the long-term impact, we're seeing agentic AI, which the previous presentation was talking about. So agentic AI is projected to grow from 2.6 billion euros in 2024 to 24.5 billion by 2030. By automating task and decision-making, they are looking to boost productivity by 20% or more. So this will likely use a SaaS or automation as a service model. And one example, well, different examples here we can see is that IBM Watson is currently automating medical data analysis for healthcare, while we have also examples like robo-advisors like Betterment, which are using AI to manage personalized investment strategies. Then we jump into the quantum computing, which is expected to grow to 10 billion euros by 2030, revolutionizing industries like healthcare and material science, with application expected to come by 2030. Their quantum as a service model will likely be used as their main business model to offer quantum computing power for specialized tasks. And also we have examples with Honeywell and IBM, which are offering this type of business model for drug discovery. We have also Biogen and Google, who are exploring quantum's potential for speeding up treatments like Alzheimer's. Then, last but not least, we have the material science AI, which will create a 10 billion euros market by 2035. Helping create new sustainable solutions and materials. Exedon is an example startup from Switzerland, which is using AI for advanced 3D printing in energy storage, and they are likely adopting a licensing or a B2B sales model. We have also examples with Porsche and Siemens, who are applying AI to create lightweight and fuel efficient materials for vehicles. So, in summary, Europe is investing a 200 billion euro through the Invest AI initiative to boost AI in sectors like biotech, climate, materials, cybersec, and agentic AI. So now let's talk about how we can all make moves to actually ensure Europe leads this race. So for startups.
And then if you can wrap up in 1 minute, please.
Yeah, okay.
Perfect.
So quickly to say, there are different programs, there are different initiatives that are taking part of this. And as we are looking to position Europe as the top leader in AI and outpass the global hubs, there are some steps that we should take. And just to wrap up, because we're ending the presentation, I have built a 2025 AI Science Funding Guide for you, so you can take a look at it and see the different actions that each of the stakeholders can take. You can also join my newsletter if you want to know more about what's happening, and you can also connect with me on LinkedIn. And I'm open to questions that you may have. Thank you.
Thank you. Thank you very much for this presentation and insightful thoughts that also show the link and the innovation loop from research, startup, investment, and the big opportunities and the big markets that are emerging from AI in science. So let's start our panel, and in which we'll have all our speakers. But I will start with the policy aspects again with Daniela regarding the AI tools. I mean, the speakers talk about what they are doing in terms of research, and then the tools, those AI agents, and so on. So the first question is, from the perspective of the European Commission, what are the funding priorities in that, and what are the policies to make this, I mean, in addition to the funding, the outcomes of those projects funded by the Commission available to the community?
Okay, so your question is broadly about the funding priorities, right? Did I get it right, Hedi?
Yeah, exactly.
Okay. If I can summarize really quickly, I would say infrastructure more broadly and talent. So on one hand, you have the very recent announcements by the Commission about the AI factories built around the Euro HPC network. So that this is for providing computational power to researchers, to SMEs. This will be further enhanced to gigafactories. On the other hand, you have the funding calls that are published every year by the Commission. As I said, basically 1 week ago, we pre-published the 2025 Horizon calls. And there you have plenty of AI to promote, for example, AI-ready data. I said that our team is pushing funding calls for foundation models in material science. By the way, maybe that will be interesting for one of your speakers, but also for your audience, that these foundation models, this specific call for foundation models in sciences in 4 disciplines. Material science is one of them, but also climate science, agricultural science, and environmental sciences. So maybe check it. So infrastructure funding calls. And something that I think is also very important, and Eden made a hint to that, investment in talent. Very recently, last week, there was this Choose Europe for Science Summit in Paris, organized by President Macron, and the President of the Commission announced a 500 million package for a super grant under the European Research Council to help offer a longer-term perspective to the best scientists, especially those who want to relocate to Europe. And there is another initiative piloted under the Marie Curie program. It's called Choose Europe, and it will provide higher allowances and longer contracts to people to scientists that relocate to Europe. And these incentives will also be targeted. Some of these incentives will be also targeted to fields like AI. So if I can sum up the priority investment, I would say infrastructure, broadly speaking, and talent.
Great. And that's important. You are talking about infrastructure because, I mean, all what we heard from the speakers and what Ismail presented regarding data, and with this grow up of data and all what we are like seeing today is thanks to this bigger infrastructure. But this is also a big question regarding this aspect. Some scientists very well known, like Yann LeCun or one of the co-founders of OpenAI, Ilya Staskiver, when they say we are reaching plateau and scaling more and more on data, that's maybe not the right solution, and we need to think about new approaches. So they are also advancing those arguments. What do you think about this, Ismail?
Well, it's on the training side, perhaps in some applications on building large enough foundation model. At some point, we might have large enough foundation models that tackle a wide range application. But on the inference side, which means during deployment time, it's actually the need to build a huge data sample is even more pronounced because, I mean, once you train the model on a large amount of data, then what do you do when you deploy them to have, robots make predictions in real time? Or even when you ask, OpenAI, GPT or Grok, there is an inference cost. Actually, recently, Sam Altman said saying thank you to ChatGPT actually cost millions of dollars in compute time. So most people forget about what is coming is even more need for compute. So, for example, DeepSeek was limited by the compute because there was the curve of advanced GPU on the on China. So, and things like this. So this does not mean reaching a plateau in training models does not mean that we will be actually not needing infrastructure. Actually, those who do not have the infrastructure will be limited into, commercializing their tools, because the inference compute, when it become accessible, it will be all the public using this, and all the applications and the AI factories, the robots, everything. So everything is doing inference all the time, 24 hours, 7/7. So whoever do not have enough compute will be limited, basically, in the deployment of these models. So when they were talking about plateau, maybe in the training phase.
Yeah, exactly. And then also this is allow me also to think about the next stages regarding how we are moving to the physical AI and the AI on the edge and the challenges that we have to deploy AI on the physical world and how to make those inference running on the edge, which is, I think, a big challenge. But also drive me to a question regarding the environmental impact. I mean, as we've seen today, that there is a lot of impressive impact of AI to improve science and so on. But there is also this large compute infrastructures had a lot of environmental impact, negative one. So how this is seen from the investment side, Eden, if you can give us an idea about that.
Hedi, could you repeat the question, please?
Yeah, the question is about what is the, I mean, that's AI is an opportunity in terms of bringing new applications and bringing solutions from the scientific perspective, but this infrastructure have also negative impact on the environment. So what is the business behind this that also we can find solutions to that also, right? There is a market for that?
Yeah, that's a good question. Actually, this is what is trying to be palliated with all the climate AI challenges that we have. The computational part of it is very important, and this is one of the points that we need to think about how we could actually keep it balanced with the data that we will need, because every year and every time we need more and more and more. So this is a great point of how we can implement this. In the investment part of this, I would say that currently what we are seeing is, well, I can speak because there is actually a German startup that is actually trying to innovate in that field. They are still in the stealth mode, and basically they are trying to speed up this process by leveraging they are trying to speed up this process by using different places and different space that is unused. And this, in a perspective of investment, this is something innovative that if we can find the sweet spot of this for the next years, I think we have one big part of the AI race win.
Perfect. There is a question from David in the Q&R, which is more for all the panel, he said, but he's mentioned some words heard a few times, he said, in the presentations regarding garbage in, garbage out. And this is maybe could be for Victor and Salim, if you can answer this question regarding the AI in research settings, and also bring me to extend this regarding the let's say the potential of making those AI trustful in terms of making science. So Salim and then Victor, if you can give your thoughts on that. You are muted, Salim.
Yeah, okay, I got it. Thank you. I think this is an important question, and I think one of the main topic is how we can trust mainly actually of the AI model. And this trust actually, this is why the one main development is the development of trustful AI. If you look at actually from the perspective of material science, the point is how you can trust a model actually that generate your data, which are not essentially based on a physics, or at least cannot duplicate physics. This is somehow actually one of the tricky, I would say, the future of the AI is to make them actually trustfully, either actually by combining in terms of validation, in terms of verification and validation. And the other aspect actually is linked how the AI are able actually to predict beyond the data space where they are trained on. And I think the other, it's an important question also how the AI model actually are able to connect with the physics. Essentially, I'm saying mainly actually from the perspective of material scientists, because this is the main question. Essentially, how an engineer or user actually can more or less interpret such results and trust mainly from the perspective of the physics and engineering. And I think this, if working mainly in terms of propagation of uncertainties, verification, essentially the link to the physics, that's actually, I think, a key research topic of the future somehow. I don't know actually if I'm answering the question you're asking actually, Hedi, but this is actually how I see things in terms of trustful AI.
Do you have any thoughts about this?
I would say also there is more and more grow in terms of what we call uncertainty-aware models. Then actually, how you can estimate mainly their own confidence in and in the data used, but sometimes actually some of the models are using synthetic data, creating data actually from generative models to fill the gap. And this is actually bring more, I would say, lack of trust in these models that are being developed somehow.
All right. So unfortunately, we are running a bit over time. So I will conclude with one question for all of the speakers and to have their concluding words about the challenges regarding adopting and integrating AI tools in the research workflows. What are the most important challenges you see? And I mean, your concluding thoughts on the topic in general. So we'll start with Ismail and then go.
Can you repeat the question again, Hedi? What are the challenges there?
The challenges like to when trying to adopt and integrate AI tools in the research workflows. And then also because you give, especially you, and a great example regarding making this research open, and then the question there also about the challenge of accessibility of this research and also making commercially viable products, to make innovation. Else, like any concluding remarks from your side, if you want, if there is no specific answer or the question is a bit strange.
I mean, the challenge I see is that we might change our way of doing research, in fact, and the fulfillment in research for researcher might be different because we have perhaps to refocus more on the creative aspect. So it's more like these are the challenges that I see. Because it's supposed to push the frontiers of research and be very helpful, in fact. So I don't see challenges, in fact, but it's more on the personal side of the researchers and the sense of fulfillment. And what we should focus on in research is trying to focus on the creative aspects more than on the repetitive tasks and these. So this shift actually, and how we train our grad students and researchers to adjust to this shift, I think the challenge is actually there rather than the implementation of these tools, because the implementation of these tools is very promising to me. I don't see how it could be damaged from that. But it's more like on our way of how to adjust to this, more like other things too. Like, for example, coding. Coding now maybe was a very hard job 20 years ago, and our generation learned to code. But maybe now, we have to adjust to the new ways of coding. And it will go for research as well, I think. And for education in general, high-level education and university education. So, yeah.
If I may say something regarding to this, I think, you mentioned the fact about, garbage in, garbage out. I think, the future will be essentially to push the boundaries to the interpretable and explainable AI, and that actually push the people somehow actually, and scientists also, to understand, but also trust the model that are being developed. I think the data is also a key aspect in terms of standardization of the representation of data, because for the moment, actually, we don't have really shared standard, essentially, about the representation of data. Ontologies essentially are developed, for each topic from the left side, but we don't have really a common representation of data. That this actually will come essentially how to bring different fields essentially to communicate and interact. because for the moment we are developing really actually AI for a specific topic, but these topics actually don't interact. And I think regarding to the curation of the data, I think this also, create a kind of how we could have a large vision essentially of building open and flexible platform that actually shared and that helped to improve collaboration mainly across the fields, not on a specific field, but actually bring medical field to the material field actually and connecting these fields. I think this might be the big challenge, and I think I personally think the novelty and the innovation would come essentially from this interdisciplinarity aspect somehow.
All right, Victor, please go ahead.
Yeah, I just think I have the things I want to say are very aligned with what the other two speakers were saying. Just want to maybe develop it further. I think research is already changing, and in general, the way we do lots of stuff are changing because of AI. We see it with our clients, with R&D personnel that are actually using AI. Things just change and will be different. But I believe that in research, particularly, there'll be a whole new discipline about understanding how the AI works, because the more we develop this technology, we'll know a bit less about how it works. And we will require a whole field at some point of people digesting and what each layer is doing. I mean, right now there is a very novel work about that Anthropic is doing on the mechanistic works of AI, which are super interesting. And so I think that this is a bit the future of maybe even of research. So we'll have much more researchers on understanding how AI works than on each and every field, because AI will be just good at these fields and better maybe than humans. And on the technical side, I think right now the biggest issue is with metrics. The moment we manage to master how to measure the final output, I'm not talking even about how the AI works, but the final output, I think there will be another jump in what the AI.
Thank you, Victor. Eden, concluding remarks.
Yeah, thank you, Hedi. So it's very interesting because you're basically talking about the technical aspects, which is true. I agree. I will provide my thoughts about the more business and investment side of this. So using AI in research, it means that you will have big upfront costs and for expensive hardware and expert staff, and you might not see the returns for a while. And basically, this strict data and all the patent rules and regulations can slow you down. And I see that turning a lab demo into a real business or a real product needs a lot of engineering support, picking the right pricing model, which sometimes can be tricky. And you also need to guide your team from all methods to use AI workflow and so on. But though adopting AI in research, I see that it could be costly and complex. But if you have like a smart planning, you have clear rules, and you have a great team support, like you can be with good mentors, with advisors, etc., you can actually turn this AI application into research, into a very profitable business and tool that could revolutionize industries or completely open new business models. So yes, there are challenges in the business aspect and the investment aspect, but they come with high reward. So it's kind of a high risk, high reward investment and business opportunity here.
That's great. Daniela, any concluding remarks?
Thank you, Hedi. From a policy point of view, I would say that a challenge and also opportunity from what we see so far is multidisciplinarity. I think this is something that Salim also mentioned, that is super important, that computer scientists and domain scientists work together, and that there is mutual understanding of each other's constraints and opportunities and the problems that can be solved together, working together. So that's one thing. And another thing that I think is very important and not so very often mentioned is trust. What can really prevent scientists from using tools is the lack of trust in these tools. So they need to really advance so that they gain the trust of scientists, and also public trust in science done with AI. You cannot achieve anything without people trusting the science that is being done with AI. Currently, the figures are not very encouraging. We have data that more than 50% of Europeans think that AI can help solve a lot of challenges, but only 38% would trust scientific inventions done with the help of AI. So I think this is something that we should keep an eye on, especially in Europe.
Perfect. So thank you very much. Sorry to being over time. Just I would like to announce that the next webinar will be on 12th of June about autonomous and physical AI. So keep in touch with us to continue discussing this hot topic. We would like to shape this future of AI, this future of responsible AI together. So we'll announce the speakers as soon as possible next week. And before concluding and saying goodbye, I would like to thank again our speakers for this nice presentations and insightful discussions. So thank you, all of you, and Jessica will just put the survey before closing to collect your satisfaction about the webinar today. Thank you.
Thank you, Hedi, and all the team for the great organization.
Bye-bye.
Bye-bye.
Thank you, everyone. Have a great day.
Bye-bye.
Yes, hello. I don't know if you can see my screen. This I will be really short and quick on that. Just 1 second, that I some problems with my sharing. Okay, and I will ask you just for some minutes more for
Jessica, we are not seeing
yes,
your screen at the moment.
I have a problem. Yes, I am sharing again. Sorry, I had problems with sharing the screens. I don't know what happened. Okay. Now you should be able to see my screen.
Yes, now we see the
okay,
screen.
thank you. So I just ask you for some minutes to reply to our survey. So you can go to menti.com, and by using that code that is up in the screen, I will now show you also the QR code to join with your mobile phone. And then, or you can enter that code, the code 61737602, or use that QR code and then go to this really quick survey. Will be divided in 2 parts. So the first part is about this webinar that was held today. So about knowledge validation and AI insight. So we will ask you what are the main gaps to develop and adopt those AI capabilities. So you are invited to vote these options that are here. So once I see that some you are replying, I will go to the next one. Thank you. I see that you are starting voting. Thanks. I will be really quick on the questions, so you can have time to look to all the questions. Okay, we'll go to the next one. So what is the most risk impact of such capable AI from your perspectives? Of course, these are closed options. So if you would like to also to comment or to share any thoughts about this also afterwards, you're invited also to our email, so to your so we can collect also your inputs. Okay, I will go to the next one. So what is the main opportunity of AI innovation from your perspective? So expanding the scope of solvable problems, and the other one, the other options that are here. Okay, sorry that I have to really to be quick because we are really out of time. So thanks a lot for the replies. So what is your recommendation for the future innovation in AI? Thank you. And then the next one. So we passed to the satisfaction survey about the organization by our side. So how satisfied were you with the content presented during the webinar? So the overall content, all of our speakers and the presentations that were used during this webinar. So thanks a lot for the replies. I'm going to this next one. Has the webinar helped to increasing your knowledge regarding the topic? So the AI in science and for science. At the end of this short survey about the organization, the webinar, you will be free to write a comment if you would like to share any thoughts. So are you satisfied with the overall webinar organization? So everything that was behind the webinar, let's say, so the organization phase of this webinar and also the previous ones, if you have attended also the previous one and the next one. Okay. And then if you would like to stay informed about our future communication, our future activities, so the EIC communities activities, Stefania has already shared with you the website, so you can also check our website for the news about our project. And then here you can share any additional comment or feedback you have about the webinar that can improve it. And I will leave it now, so you can also write any comment in the next future. Thanks a lot. I will now stop my sharing.
Thank you, all of you. Thank you, Stefania, Jessica, and sorry that we are running out of time. Thank you for all of you, and see you next time. Bye-bye.
Thank you. Thank you very
Thank you.
much.
Bye.
Bye.